Okay, I think we can resume. So the second talk today will be given by Harriet Walsh from ENS Lyon, and she will talk about Hermitian Schur measures.
Okay. Thank you, and thanks to Filippo and to the other organizers. It's really nice to be here. It's the first time I'm here, and I can see why people talk about it so much. So I'm going to talk about, well, Hermitian Schur measures, which are just an extremely simple way of choosing a well-defined Schur measure. That in the cases we're interested in are, I suppose, somewhat unpopular among people who look at Schur measures. You wouldn't want to pick a Schur measure that way, but in particular, I'm going to talk about joint work with Dan Betet and Jeremy Boutier, where we managed to find something quite interesting with this kind of construction. And then at the end, I'll talk about something also weird that can happen with this very simple setup. So, oh no. I was sorry. Okay. Perfect. Thank you. Yeah. So what I'm talking about in general is just a way of inventing nice measures on integer partitions. Probably don't need to be defined, but here's a definition anyway. They're weakly decreasing sequences of positive whole numbers, which we represent graphically with Young diagrams, where you stack rows of boxes corresponding to the parts. So in the English convention, we do them this way, but I'll mostly use the French convention. I think the population we have here maybe justifies that. And anyone else, I hope, will forgive me for that. And perhaps the most natural way you define a measure on partitions is to do with connections with permutations. So on partitions, with parts add up to n, partitions of n, there's a natural measure that arises from considering uniform random permutations and the Robinson-Chenstead algorithm. So if you take some permutation of the numbers 1 to n, you apply a bijection, or you apply the Robinson-Chenstead algorithm to shuffle each element into a pair of Young tableaux. Those two tableaux have the same shape. And this induces a measure on probability that the shape of some uniform random permutation via the IRSK algorithm will be a partition lambda, called the Plancherel measure. So this is a very classical result, and the main properties we have is that when you look at the Young diagram of a Plancherel random partition, see this deterministic lemon shape, it's found by Vershik, Kirov, and Logan and Shep independently. And of course, what's particularly interesting to me is that it's a particularly simple solvable model, kind of in the KPZ class. So when you look at the fluctuations around the edge, they have this 1/3 scaling. This is a theorem of Bijkdef and Johansen, very classical result, where, yes, we find that the fluctuations are driven by the Tracy-Whittam distribution. It also drives the largest eigenvalue of Dewey random matrix. And normally how you kind of look to generalize it is via the permutation side of this. So this result equally applies to statistics of uniform random permutations. You can interpret a uniform random permutation geometrically by just drawing out each element on a kind of grid. And then the longest increasing subsequence, that data by the Robinson-Chenstead bijection in this case is just the first part of the shape of the tableau that it outputs. So the statistics for the first part of a Plancherel random partition just give you the statistics for the longest path in some kind of uniform random media. This is the simplest case, and the typical way you'd want to generalize it is to consider, for instance, more interesting media. So this is something I mentioned in Guillaume's talk. I tried to pick that example on purpose, where you naturally find, due to the symmetry of this situation where you look at paths conditioned on arriving at a certain point, a measure built from a particular family of symmetric functions called Schur functions. So here the Schur functions will be in two sets of variables, A and B. where A and B should be between 0 and 1. And that'll give you geometric random weights on your lattice. So this is the kind of typical thing you have, and then you can also make this time dependent. You can, instead of putting a measure on partitions, you define this so it's a process on interlaced partitions. And the structures that let you solve this actually come from how nice these symmetric functions appearing here are. So you can define Schur functions in various ways. If you prefer determinants, you can write it as a kind of ratio of a van der Waals determinant to a sort of shifted van der Waals determinant. If you prefer counting things, you can just specialize the parameters by counting the number of appearances of the labels in a standard semi-standard adjunctive load. So where you lift the condition on having strictly increasing entries on the horizontal rows. And these are also nice in other ways. They're an orthogonal basis as well for the symmetric functions. But we're going to be interested in a case where we don't look at processes at all. So instead of using something which refers to the symmetry of these functions directly, it's really just the determinantal structure that we'll be exploiting. In particular, because we set these up directly as lattice fermion models. So from quantum mechanically, we define the determinantal point process and don't worry about having a well-defined process in time, or stochastic process. And the advantage to this, to say what our main result of this will be, is that we were able to define measures this way so that you could escape the KPZ universality class, or in particular, instead of having the Bach-Johansen edge behavior, which is generic for much of last passage percolation, for instance, or other processes, we can get this kind of behavior that was studied by Pierre Dussel and Gregory Schur for momentum of trapped fermions in the first instance, where you have, instead of 1/3 power, you have a 1/2m + 1 power. And where instead of the Tracy-Woodham distribution, you have this very natural higher order generalization. So here, rather than having a Fredholm determinant of the area kernel, we have a natural generalization of the area kernel. So with that introduction done, I'll explain what Hermitian Schur measures and I'll talk about are, and then talk about exactly that result and how this corresponds to something that came from physics, and also the advantage of using this more algebraic approach with random partitions. So first to say what I mean by Hermitian Schur measures in the first instance. So why Schur measures are solvable in the first place is because they define a determinantal point process on not quite the partitions, but these ensembles of points that you get by rotating the French-Young diagram to anticlockwise by 45 degrees and then reading the slopes of the top off. So we'll consider these as points on the half integers, and in particular as fermion configurations. So starting from a domain null state, which will correspond to the empty partition. Anytime you have some other partition, you excite particles to the right or move particles to the right of that state for each part of the partition. And each of these states, we can just notice that they're eigenstates of a Hamiltonian with the linear potential. So the linear potential means that you have all of the sites filled to the left and all of them empty to the right. It's all of the half integers here. So perhaps not the most physical setup, but with this kind of Hamiltonian, if we have an infinite number of particles in the state, we can consider its eigenstates. And continuing this kind of second quantization route, we can then generalize this linear potential a bit by adding kinetic coupling terms. So something that creates sort of nearest neighbor and then next nearest neighbor and further actions. So for the R, it's between the rth nearest neighbors. And we'll add these via a unitary operator, which is this u, which is going to be the exponential of sum of unitary, so of AR dagger, which will have R steps to the right, with some complex parameters TR, which for our sake we'll just always take to be finite, which has some kind of physical sense. We're never considering very long range interactions, only ever some finite range. And with this unitary operator, we get another nicely defined Hamiltonian. It's this one here. And when we look at the ground state, actually we were just evaluating these fermionic operators on the state, and from fermion calculus, in fact, we're pulling out Schur functions. So if we want to decompose it on the eigenstates indexed by the partitions, we're just getting a sum weighted by Schur functions. And the role of the parameters that we selected, the TR, are not the normal specialization for the Schur functions. They're a specialization of the power sums, or the mu times, as we call them. So if those power sums, there'd be a factor of 1 over R then. We'll just consider it this way. So since we're taking a finite set of mu times TR, means we're always, the underlying specialization of the Schur function is always with an infinite number of parameters. And in practice, it's not a positive specialization. But, well, it's a very natural physical system, because to begin with, we can look at what the potential looks like in this bosonic operator, so with the hopping terms, and it's just a sum of harmonic oscillators, or a collection of harmonic oscillators together. Then these terms here, these kinetic hopping terms, can be thought of as just kind of dilation in momentum and position space in our dimensionless setup. And if you look at the ground state, so this superposition of partition labeled states, it's just a coherent state. And meanwhile, back on the partition side, because we have something generated by Hermitian Hamiltonian, we have a well-defined probability measure on the partitions, in spite of our weird choice of specialization. And then this is as introduced by Ukhunkov, Schur measures are always something that defines terminal point processes, meaning that if we, rather than looking at the probability of having this kind of full infinite set of sites given by lambda, which quantum mechanically, I guess, wouldn't really make a lot of sense. If we just look at some finite set, we're always of sites, so of half integers that we read off the partition like this. The probability of finding them in the given partition is just going to be the determinant of a kernel, and we have an explicit generating function for that kernel, which is particularly nice because of the structure of the mu times here, or because they're expressed in terms of mu times and zero value. So the simplest case of this, where we just said the first mu time to some parameter theta is very well known. It's the Poisson's Poisson measure. And when we evaluate the probability, we see that it is really just the Poisson measure. So the number of young tableaux and the size of the partition being taken is no longer fixed to n, but it's a Poisson random variable of parameter theta squared. And this has a perfectly good combinatorial sense when we think of what the operator A1 does, because this is the one that's shifting a particle one site to the right. So if you are getting from the domain Walt state up to a partition, the state level by partition lambda, it means you're actually counting all the ways of getting there, or in other words, you're counting ways of filling the boxes of the Young diagram with increasing numbers up to its size. So you're counting the number of standard Young tableau. So to look at the justification for why we want to go beyond this Plancherel case, we were motivated by this paper by Pierre Gagri and Satya Majumdar, where they considered what else can happen for fermions on the real line in confining traps. So here they're in continuous space. They use first quantization, and they consider particular confining traps that look like x to the 2m for some m. Although, yeah, some positive integer m. And what happens in position space is exactly the universal case where you expect to get the area ensemble, which then gives you the Tracy-Widom distribution, because you're going to linearize the potential experienced by the particles there. And meanwhile, the kinetic part will just give you the second derivative, and the eigenfunction of this, or one of the eigenfunctions of this, is an area function. But if you switch to momentum space instead, and you look at how the momentum will fluctuate around the Fermi momentum, you get something very different. And this term, this p, plus minus 1 to m with the 2mth derivative in p, will have these very natural generalizations of the area functions as their wave functions, and in turn the ground state correlator is just given by something built up from these generalizations of the area functions. So here it's just the kind of upgrade is, instead of having a power to a power of 3, you have a power of 2m plus 1, and the rest of the factors change in turn. And the fluctuations that you get around the Fermi momentum are just built up from precisely these kernels, just determined in this kernel. So the marginal distribution looks like that. Sorry. And this also generalizes a connection with classical integral differential equations. In the case of Tracy-Widom distribution, you have an expression in terms of the solution of Pan-Lavey 2 equation. And here it's the mth equation in the full Pan-Lavey hierarchy, which is satisfied by this. So this is proved, the equations were derived in Majumdar and Scher's paper, and then it was proved that exactly the kernel they had found was the solution to these higher order Pan-Lavey equations by Professor Claisen-Girotti afterwards. And in the original paper, they recognized with these equations that they'd also appeared in some work on unitary matrix integrals from the 90s. So Pavel and Chevitz had defined matrix models that are kind of analogous to Kazakov's multicritical matrix models. So they had particular edge behavior and vanishing of order 2m, and using some kind of orthogonal polynomials method, they were able to cook up something that would be multicritical and would satisfy these higher order Pan-Lavey equations. And just to note as well, all of this both on the kernel side and on the Pan-Lavey equation side has been extended to finite temperature, although I won't talk about this. So what we found is, and it's perhaps not at all surprising because of the fermionic setup, we were able to tune mu at times to get exactly what should happen on the edge. So for instance, here's some things that we can put into, we take a single parameter that'll control the size of partitions. We'll multiply each of our mu at times by that parameter. That defines for us this kind of a measure, and say we can just take some particular rational coefficients like these, sample things, and what we find is that you have a limit shape that, just as with the momentum density studied by Majumdar and Schur, we have a vanishing coefficient that generalizes the Wigner semicircle law. We've got coefficients of 1 over 2m rather than 1 over 2. These should be m too, I'm afraid. And this is also, this kind of limit shape is also recovered in a kind of time-dependent free fermion process by Severio Vicini and Germain Stefan, the same year that we were working on this. Although again, the setup they had wasn't a time-dependent process. So this kind of behavior seems to be uniquely related to these kind of fixed time quantum mechanical models. And I put the wrong diagram here, so it doesn't make any sense. Sorry, you can also, if I put in the right figure, you would see that if you want, you can take only odd labeled integers and you'll get something symmetric. So both of the edges will vanish with a 1/2m factor. And you'll have, in particular, this edge behavior that I'll talk about now. So we were, of course, more interested in really the universality classes that would correspond to this higher order Tracy-Woodham distribution. So if we want to write sort of the broadest conditions we can have, we just took some finite set of at least m parameters that should set this set of m linear equations. One of them just sets a coefficient b, another just sets a coefficient d that we need in our theorem, and an extra condition here that makes our proof work, basically. In particular, first the momentum spectrum associated with this. And with that, we have exactly this higher order generalization of the Beck-Deschner-Johansen result. And we also have a finite temperature version where we get exactly the finite temperature kernel by extending to cylindric partitions, where introduced by Borodin and then translated into more fermionic language by Dan and Jeremy, who worked on this project too. And this is something that we kind of knew we should be able to do, because this tuning that we do, or exactly this set of equations that we have here, just corresponds to finding some weights such that our Hamiltonian will look exactly like the Hamiltonian found by the Majumdar and Schur when we take both a continuum limit, which also corresponds to the large scale limit. So when we take our one parameter theta going to infinity. And this is also around the same time, or the same week, I think we put a paper on the archives. Someone else did similar analysis, Kimura and Zahavi did a similar analysis where they just looked at the wave functions associated to a discrete Hamiltonian and found suitable ones that they correspond to the higher order Airy kernels in that limit. But rigorously, what we did was we looked at what happens with the kernel. And here, having this order m multicriticality means that the asymptotics we're doing for the kernel. So here we just have like an action, and it's kind of a path integral as theta goes to infinity. We're just finding some third path here. Means that in this case we're going over an order 2m saddle point. So I thought it would be nicer just to show what that looked like literally. So what you're computing when you have one of these kernels, so in the Plancherel measure case, you have kind of two saddle points that you're computing, and when you're in the bulk, they're on the unit circle. And this will give you some probability of having a point between 0 and 1. And then you get frozen regions either side. So here you have fully occupied sites, and here it corresponds to empty ones. And when you go to higher orders, you just get more saddle points appearing. And on this multicritical edge, what's happening is that they're all coalescing together. And it's this higher order of criticality for that critical point that gives us what was called multicritical already by some of the and Schur, this kind of property. So now I think it's all of that was just true for fermions. So I want to justify why it's interesting to treat this with partitions. And really the interest is that it comes back to that apparently coincidental connection with unitary matrix models studied by Perryville and Shevitz, because that was only an asymptotic connection. So for large matrices, you found these higher order Planck equations. But here we find that the same connection holds pre-limit. So without going to any asymptotics, we find the marginal distribution, the cumulative distribution for the first part of our partition, using some classical identities is just equivalent to a unitary matrix integral. And this amounts to just the Cauchy-Binet identity for the Schur measure, where we have the same set of parameters taken twice, which just gives an expression with a Toeplitz determinant, and then Toeplitz determinant can be kind of Fourier transformed to give us something in terms of points on the unit circle, which is just a unitary matrix integral, in fact. And when we use the particular specialization I showed first, where you just take the simplest, we take some m points, or some m coefficients that satisfy our multicriticality condition. This gives us exactly the matrix model they found. So kind of the simplest way of getting multicriticality on both sides, you get the same, you get exactly the same model. And this is something, so in the Poincaré case, it's the connection with Gross-Witten and Widia model, which Johansson used, or identified and used. And it also kind of changes this. There's, in that case, an image of a phase transition, and it changes the nature of the scaling associated with that transition in this case. This would be an exponent of 2 plus 1 over m in this case. And also this gives us kind of a hint at how we might get combinatorics back out of the model, because what they were doing when they were suggesting these unitary matrix integrals was, idea was to generalize work on random maps using Hermitian matrices. And here we have two things that are very naturally connected to the enumeration of surfaces, both partitions and matrix integrals. So just finally, I'd like to talk about one direction, which I think is quite interesting, which is to lift that extra condition I had at the end of a definition of our multicritical measures, which interestingly doesn't seem to be necessary for the heuristics. So this extra condition we need on our coefficients doesn't appear naturally if you just want the Hamiltonian to look nice, or for its wave functions to appear to resemble Airy functions. But what it does do is it gives you a single connected support for the momentum spectrum in the ground state. So situation where you remove this condition is called you can call it a split Fermi C from work on the Lee-Vinegar model by Elians and Co. And this is also treated in Silas Elian's PhD thesis. And more recently, for the fermion case, I think the first people to really do it was Sylvain Vicini and Jeremy Stefan, who found limit shapes in a particular case where you can identify that here, once you remove this condition, you have a kind of cusp. So internal cusp within the limit shape, and this you can still treat as before on the partition side, which is on the kind of Schur measure side, and with the same technology, so the Brodin, Okun-Kevin-Olshansky method for looking at asymptotics of kernel. But in this case, say just in the simple case that they found here, we actually find something quite weird happens. You find when you look at exactly which, where the saddle points go in this case. So here on the left-hand side, it's the sort of normal occupied state, and then we have two saddle points on the unit circle, and then we reach a situation where you have a cusp because you have this critical point on the right-hand side where two are coalescing. But now on this right edge, it's actually 2 points where multiple saddle points are coalescing. And when that happens, we aren't getting any of the Fredholm determinants we've looked at already. It's a very slightly different one, which is still a well-defined Fredholm determinant and a well-defined distribution, but seems to have this almost spatial decorrelation type behavior. And also in this case, we get something kind of non-universal for the bulk behavior too. So to conclude, this is some further things we can look at. One thing, so everything was extended to finite temperature except for this connection with unitary matrix models, where when you write this down, you maybe if you know enough determinant identities, you can get something sensible on the unitary matrix model side. I think it's something interesting to look at. And there's some further things. So on the kind of more analytic side, I'm trying still to extend this to non-integer n, which was already done for multicritical Hermitian matrix models. And then also the kind of cusps you see, these split Fermi C models also quite interesting. And then finally, this question of, can we get some combinatorics out of this very non-combinatorial model? So thanks very much for your attention.
Are there questions?
So in the second last slide,
Yeah.
in the definition of the kernel, I wanted to understand this kernel A tilde.
Sorry?
Next slide.
Oh, yeah.
I wanted to understand better the definition of this kernel A tilde.
Yeah.
On the right hand side, x equal y, x equal y.
Oh no, that's
Less
x not equal to y. Sorry, that's very much incorrect. When it's not equal, it should be. Yeah.
So what is the?
So it's when x is equal to y, you have the normal one, and then you have a factor of half once they are apart. So you get more decorrelation spatially than. And this, by the way, isn't the actual. It's not the kernel you get directly. It's kind of an effective kernel that appears in Fred Amsterdam. Does that make sense?
Can you comment on this finite temperature extension? What will change in your measures? What do you expect?
So as like the unitary matrix side, so I guess you have a.
When you define your measure on a partition, which is just a weight of the excitation, particle Hall excitations, you're acting on the ground state to create a Schur function. So I'm just wondering what is the finite temperature
okay, so it's still I think still quantum mechanically is still a ground state, but there's sort of a mixing or actually I don't entirely know. I only kind of know the partition side, if I'm honest, where basically you have
mixing means not the wave function, but rather the density matrix. That's what you mean?
Oh, no, so at the kernel level, you have this kind of 1 over 1 plus beta to the, sorry. Or, yeah. Sorry.
Yeah, I will relate it to this finite temperature extension that you mentioned. Do you have, I mean, in mind this kind of Moshe, Neuberger, Shapiro model or generalization of it to this multicritical case? I mean, for the, I mean, if you just look at the standard case, say m equals 1, I think, in your, then there is indeed that finite temperature. There is a matrix model actually that corresponds to it.
Oh, okay.
Which is this Moshe, Neuberger, Shapiro model. And I was wondering whether when you wrote, I think you wrote explicitly a finite temperature generalization of the multicritical matrix models. I was wondering whether you had these kind of things in mind or something else.
So I didn't know that this is a unitary. Yes. Yeah. Okay. Yeah. So I've just been looking very literally at what you can do with some algebraic identities with the expressions you get from cyclic partitions. But yeah, I should. Thanks. I should check.
Okay. If there are no further questions, let us thank Harriet again.